It's great to be here, and we have a beautiful lineup this afternoon, actually, in terms of material to discuss. We'll start off with John Einmahl, standing over here. John is an acclaimed researcher who published two papers in statistical journals on extreme value theory, actually in 2009, the Annals of Statistics and the Journal of the American Statistical Association. He will introduce us in a world that helps us understand what is the most extreme value and how far is a current value away from such a maximum. And I'm very curious about what you're going to say. And the floor is yours.
Thank you. Thank you very much, Jan, and also Peter, who's not with us yet. I'm very grateful for this invitation. It's very special for me to talk here, also very challenging. The main purpose of this talk is to provide you with some tools and some thoughts about extremes. This is only an introduction, although I have 50 minutes, I think. It's quite long, but it's only an introduction which I will present now, and I'm quite sure that what I'm telling that it is not exactly tailor-made for the questions you have. So I think that some work has to be done. But I hope that an adaptation of these methods can be useful for some of your research. Actually, a main message of my talk is that if you want to do tail inference, if you want to do inference for the tail of a distribution, so about extremes, you should not use the bulk of the data, you should not use the central part of the data, but you should only use, say, the 100 upper order statistics or so, so only use the near extremes. So my talk consists of 5 parts. First, I want to give you an idea by some questions what I mean with extremes, because there were several talks about extremes, and it seems that we don't have all the same definition. Then I start with an introduction to extreme value theory. Then I go to predicting or forecasting the ultimate 100-meter record, because that's what's in my title. So it's about athletics, not about accounting. But that's probably why this research got some attention.
Thank you, John.
I discovered being a mathematician, doing highly technical stuff sometimes, that athletics or sports in general is a very sexy subject, and that it's read by many people. After the athletics, we go to some other extreme events related to finance, insurance, and so on. And finally, we will look at more than one variable at a time. So we look at dependence of extremes or tail dependence. So it's clear that we often talk about forecasting extreme events. And central to this lecture, as I just said, is the question how fast how fast humans can run. Not in the year 2525, when we are all dead, but soon, tomorrow. And to make this more precise, we will consider the 100 meters, and we will look at men and women separately, as we should. But let's look at some other related problems, but in very different fields. So a question you could attack with extreme value theory is what will be the total loss, the total insured loss of the first hurricane topping Katrina? Another question which is actually very relevant in the Netherlands is how high should the Dutch sea dikes be in order to protect us against extreme water levels? And there the formal number, the formal probability which is given to us is a yearly probability of 10 to the power minus 4. So we want the probability of a big flood, like the one we had in 1953, to be we want the dikes be so high that this probability is 1 over 10,000. Another question, although the answer is in the Bible, how long can humans live? Or, and this is one of the papers which is in the conference material, which monthly performances of airlines are extremes? The question asked to us here was to have a kind of signaling system to give warnings to airlines if they have an extremely bad performance. But how do you find this? Actually, the probability which was associated with this warning was 0.15%. So it's about 1 over 600. More finance related, how much can we lose on one day on a certain portfolio of stocks? And again, you need to associate this question with a probability, so say disregarding once in 1,000 losses. What can we say about extreme precipitation levels or extreme wind speeds or other climatological quantities? More in economics, what's the price of an object at an auction, because there it's also the extreme level, the extreme value that matters. What's the maximal possible production of a firm given certain inputs like labor and so on? So estimate the efficient production frontier. How large, and that's my final question in the introduction, how large should the capital buffer of a financial institution be to be used in bad times? Okay, so extreme value theory. What we assume is that we have data, let's call them risks. They have some, we call them x1 up till xn, n is the sample size, and let capital F be their distribution function. So it means that the probability that one of these risks is less than or equal to A is f of A, right? So that gives you a nice, hopefully smooth, increasing function, the distribution function. Let's also look at the inverse of this distribution function, which is the quantile function. So if you pick probability, call it U, and then you look which level corresponds to this probability, then you call this the quantile of U. It's a well-known definition. So if f of A is U, then Q of U is A. That's just the inverse function. And our interest in this talk is to consider or to estimate the Q for a very high probability. So that means if you start looking from the top, that you have a very small probability. So you look at the quantile, at the inverse distribution function at 1 minus p. So that means at the level 1 minus p, where p is very close to 0. So if you want an absolute number, you can think of 1 over 1,000 or 1 over 10,000 for the p. If you want to relate it to the sample size, you might think of probabilities p, which are, say, of order 1 over n or even smaller. So that means that you need extrapolation. And what's quite crucial is that we do not want to make parametric assumptions on f. So we are not assuming that this distribution is normal or exponential or whatever might be your favorite distribution. Because if you assume this, and even if the central part of the data seems to fit well this distribution, it might be that you in the tail get a very bad fit and that you therefore come up with very bad estimates. I'm always looking at the right tail of the distribution, so at large values. If you want to look at the left tail, like in case you have negative returns, for instance, then I just flip it over to the right tail by multiplying with -1. If I look at times, for instance, in running, then also you look in the left tail of the distribution, but then I look at speeds. So if the time gets shorter, the speed gets higher, and then I'm back in the right tail again. Well, the question is, can we do that? Can we do, say, extrapolation? Can we look at values q of 1 minus p without any assumptions? And the answer is, unfortunately, we cannot do that. So we need something. If here is my highest observation, and I want to forecast something over here, and there is something very strange going on, if this distribution function has very irregular behavior, then I cannot do extrapolation. So what we assume is the so-called domain of attraction condition. That's quite technical. I will not go into the details there, but we want that f is in the domain of attraction of some extreme value distribution, as it's called. This is a very weak tail regularity assumption, so it assumes some regularity in the tail of the distribution, and it basically includes all known textbook distributions and many others. So if you believe in the normal distribution or the exponential distribution or whatever, it's just a very small subset of the large class of distributions f which satisfy this domain of attraction condition. Now, if we assume this, so we assume some regularity in the tail of f, we can do mathematics, we can do some calculations, and we can prove then, so that's not something we assume, that this limiting distribution function g, that is basically determined by one parameter. So g is a distribution function which depends only on one parameter, which we typically call gamma. Gamma is a real number, and this gamma is called the extreme value index. And this extreme value index is very important in my talk. So it basically says if we assume this weak tail regularity assumption, then there is some number gamma which characterizes g, but since there is a relation between f and g, it also characterizes f. Yeah? So we are not interested in g. G is something auxiliary, but if we know gamma, then we know g of gamma, and then we also know something about f, and also something about these extreme values q of 1 minus p. Let me try to explain a little without using slides full of formulas what this extreme value index is. So the extreme value index measures the tail heaviness of the distribution function. The larger gamma, larger this extreme value index, the heavier the tail. So a large gamma means that a distribution is risky. Low gamma, like a small gamma, negative gamma actually, means that the distribution is, let's call it, tame. So what do you see in this picture? In this picture we have 5 data sets of size about 1000, and we took only the top 50 observations from these about 1000 data. So we have a largest value, we have a second largest value, and we go up to the 50th value. And now we depicted them in such a way that the observation, if you start counting from the top, observation 26 up till observation 50, that they have the same range. They are measured in very different units, but that doesn't matter. So it means that in all the pictures, if you go from here, this is observation 50 to about observation 25, they are all on the same scale. They have the same scale for the 5 data sets. And now what you see is that if you look at the first data set, that it's spread out very much. It has a heavy tail. The second one, it's still spread out a lot, but not that much, and so on. And you see that the 5th data set is the most tame data set in a sense. The first 2 data sets are simulated. They come from distributions with a gamma of 1/4 and 1/8. And the 3 other data sets, they are from athletics. The middle one, so the 3rd one is from the long jump. And the other ones are from the 1500 meters and the marathon. So you see that the marathon has the lightest tail. The first distribution with a gamma of 1/4 has the highest tail, the heaviest tail. let's look at it in a different way to give you some idea what these numbers mean. So if you look at stock returns, negative stock returns, and flip them over to the right side, then we typically find gamma values, so values for the extreme value index of around 1/3 or 0.3. If we look at exchange rate returns, we find a gamma of about 0.2. So the tail is a little bit less heavy. If we, for instance, look at fire insurance claims, then the gamma we typically find is between 1/2 and say 0.7 or 0.8. So it's a very heavy tail. Actually, if gamma is larger than 1/2, then the variance or the standard deviation of the distribution doesn't even exist. So it's meaningless to talk about 2 or 3 sigma. Fortunately, in the finance case, the data are a little bit nicer, but still they have a relatively high extreme value index. If you look at water levels at the Dutch coast, gamma is negative, but very close to 0, like -1/20. If gamma is negative, it means that the distribution has a finite endpoint. If gamma is positive, it means that the distribution doesn't have a finite endpoint, at least from a mathematical point of view. If you look at the normal or Gaussian distribution, which is a very important distribution in modeling, then gamma is 0. It's always 0, whatever mu and sigma you take, whatever standard deviation you take. So that means that this normal distribution is very limited for dealing with tails. It basically gives you all the time the same tail behavior. So if you have if the data come from a distribution where gamma is not equal to 0, yes, then it's kind of useless. But it's maybe good to have a quote of Alan Greenspan back in 1995. It says, among others, that from the point of view of the risk manager, inappropriate use of the normal distribution can lead to an understatement of risk. So that means that you underestimate the quantiles. And this can be very wrong, not just a little bit wrong, but very wrong for some data sets. And at the end, improving the characterization of the distribution of extreme values is of paramount importance. Let's, for the time being, assume that gamma is positive. What does it mean, gamma is positive? It means that you are in the heavy tail case. It's the most interesting case. It's the most risky case. Also, from a didactical point of view, gamma positive is the easiest case. So mathematically, it's the easiest case. If you have that F is in the domain of attraction of G, our basic assumption, our very weak assumption, then we can infer from this, and I wrote it down a little bit sloppily. You could write it down more nicely with limits and so on, but this is easier for understanding. We find that a quantile at an extreme level, so at a level 1 minus p, is approximately equal to a quantile at the less extreme level, but still extreme level, multiplied with some factor. So this is the basis for our extrapolation. So it says that extreme risk levels can be obtained from somewhat less extreme risk levels. What's k? K is an integer which is relatively large in itself, but which is small compared to the sample size. So if you have 1,000 observations, I'm thinking of large samples, then k is maybe 50 or 20. So that means that here you're in the data, but still in the tail of the data, and here you are typically outside the data. So that's the extrapolation step. And we are doing statistics. So everything which we do not know, we give it a head, we estimate it. And what don't we know in this formula? We don't know the quantile at the level 1 minus k over n, and we do not know gamma. We know k, we can choose it, we know n, it's the sample size, and we know p, it's given. So we do not know, know the Q of 1 minus k over n, and we do not know gamma. So we give them a head, and this gives us a way of estimating an extreme quantile. The estimation of the 1 minus k divided by n quantile is easy, because we just estimate it with the corresponding order statistics. So we order our risks from small to large, and we take the k or the k plus first from the top, which is the n minus k from below. So that's easy. The estimation of gamma is quite complicated, and there are several estimators for this. One is the Hill estimator. It only works for positive gamma, so it works in this case. There is also the moment estimator. There is an ML type estimator, and there are more estimators for gamma. What's important, and unfortunately not easy, is to choose a good k. So the question is basically what's tail and what's central part of the data. So where does the tail start if you come from the center? I will not go too much into this, but there are methods for finding good k's. If gamma is not if gamma is not positive, so if you want to look at a general gamma, you can actually generalize the formula we just saw, but you may forget that immediately if you can. If you look at the general formula and you plug in p is 0, then it's not so hard to show that from this long formula you get the shorter formula, this one, and it gives you an estimate of the endpoint of the distribution. So 1 minus p gives you a certain level, a certain high level, but it might be that the distribution has an endpoint, which is the case if gamma or gamma head is negative. So if gamma head is negative, then you can estimate the endpoint of the distribution, and you get this just by plugging in p is 0 in this long formula. And this we will use actually to predict or to forecast the ultimate 100-meter record. And that brings me to the third part of the presentation. So what we want to know is how fast a human can run the 100 meters, and we want to know the answer for what happens in the near future, so not in the year infinity. And there are two approaches. You can try to model human performance by looking at biomechanics and these things. I'm not an expert in this, but you also can just use the data, because you say all this bio information, it's in the data. What people typically do, and what you see in the newspapers, if there is a new world record, what they do is they make the following plot. On the horizontal axis you take the calendar years, and on the vertical axis you take the present world record, and you put a dot there if the world record is improved, and you fit a regression line, a regression curve to these data. So the red line is a linear regression, the blue line is a parabolic regression, and a problem here, that's on the next slide actually, is that you only use a few data, 20 or so. That's not good from a statistical point of view. And also if you have a new world record, then it might change the forecast substantially. It also depends very much on the type of curve you choose, as you could see from the previous slide. And what's also not so good of this method is that if you want to forecast how fast somebody can run in up till 2010, up till until this year, or until 2011, that you see that both forecasts, both the red and the blue line, that they are very much above the present world record of 9:58. So it doesn't work. What do we propose? So again, we want to predict what's possible, say, this year. And we consider the 100-meter times from 1991. This was the year that modern doping control was introduced. until our data collection ended, which was the summer of 2008. And we took the personal best of every athlete. So we looked at the best personal best, which is in principle the world record. Then we looked at the second personal best, and so on. These are our data, or our order data. And we will use these personal best to obtain information about the ultimate personal best, which is the endpoint of the distribution, the ultimate world record. And the advantage of this approach is that we have much more data than if we use the naive approach, say, which I showed in one of the pictures before. This is what we found. So we collected as many data as we could, but we didn't want to have holes. So for the men, for instance, we found 762 personal best. So that means that number 762 is really number 762 of the world. So these are not just 762 personal best, but these are the 762 best personal best. So the best time in this data set is 9:72, and the worst, but it's still extremely fast. We can try it in the break after this lecture. It's 10.3. For the women, it's a similar picture. We have a few. We have not that many data. 479. The best is 10.65, and the worst, again between quotation marks, is 11.38. If you know the world records, you see that they are both not in the table, because the world record for women was set before our data collection period, 1991. It was actually set in 1988. And the men's world record, 958 of Bolt, dates from summer 2009, so it's set after 2008. But that's not a problem. The nice feature of our method is that it hardly changes, that our prediction hardly changes if there are new world records. So the main thing which we need to estimate is to estimate to estimate the world record is to estimate the extreme value index. So we need to know the heaviness of the tail of this 100-meter distribution for both men and women. And what you see here, and that's something I should explain carefully, it's a plot of the estimator. Actually, there are three estimators, but they look a little bit similar. One is the solid line, one is the dotted line, and one is the dashed dotted line. But again, they look a little bit similar. And we set them, we plotted them as a function of k. So if you, for instance, look at the value 100, that means that you take the top 100 personal best to estimate gamma. If you look at 300, you take 300 observations, 300 top order statistics. And now the question is, where should you sit with your k? And we have used several methods to find this, and we also averaged out a little, and what we found is a gamma head of minus 0.19 for men, and almost the same value for women, namely minus 0.18. So that means that the gamma, the extreme value index, is small compared to the other examples we saw, the financial examples and the water levels examples. So that means that athletics, 100-meter performances, that they have a very light tail. So that means that nobody can run the 100 meters in 5 seconds in 2010. With stock returns, if you watch this for 100 days and you have some loss, then it might be that the next day you have a loss which is twice as big. This cannot happen with athletics. And this is what this extreme value index tells us. So what did we find? We find 951 for men, and we find 1033 for women. And the 958 and the 1049 are the present world records. I also converted it to speeds in kilometers per hour. It's not so difficult to change this to miles per hour, but I will not try to do that by heart. And what's more important is that these are estimates. We are doing statistics, and we are doing statistics at a very in a very risky way, because we are extrapolating. Yeah? So in order to tell you something about the quality of these estimates, we were 3 times right. And if we do that, we find for the 100-meter men 9:39, and for women 10:15. As I said, if you wait a little or change the data a little bit, then you basically get the same forecast. So a new world record doesn't influence our results very much, which is good, of course, because you should have a stable method. What's maybe interesting is that when you saw this from the table before, when we ended our data collection, the world record was 972, and we predicted for the man an ultimate world record of 951, which was far away from this 972. So people didn't believe that, and they say there cannot be such a big jump in 1 year. But fortunately, Usain Bolt helped us, and he improved the world record in 1 year from 972 to 958, and that's pretty close to what we predicted. Being a mathematical statistician, I typically write papers with a lot of formulas and so in them, and this is hopefully read by some of my colleagues, but this was something very different. So when we published those results, even as at a preprint, the news spread immediately over the world, which was very surprising for us, and also quite nice. So we tracked it a little, and we found it in at least 70 countries and like 1,000 newspapers and magazines and so on. So it was completely different from what I was used to with proving all kinds of complicated things which were only read by a dozen of people. An extreme experience. So now let's go back to the general situation. So I mean, let's forget about athletics. So this was our formula for estimating high quantiles, and without going into details, this can be used in many situations in finance, for instance, or insurance. So you can use this for estimating value at risk, or even more extreme levels used for stress testing. But also this can, in principle, as a basis, because there the situation is more complicated, be used for estimating capital buffers, like economic capital, where the P is typically something like 0.0003, or regulatory capital. Instead of trying to explain all this, let me give you one more example. Here we looked at the exchange rate, US dollar against euro. We took data of the last 6 years, about 1,500 data. So roughly half of them were positive and half of them were negative. And first we look at the right tail, so that means that the dollar gained value. And you see you get a very nice plot if you depict the quintile estimate as a function of k. It hardly moves as a function of k as long as k is less than 400. And I have not applied precise methods to this to determine k, but you immediately see from the picture that an estimate of 0.027 seems to be quite reasonable. And here is the other picture where you look at, this is a situation where the dollar loses value. This picture is a little bit more ugly, but still for k running from 0 to 100 or 200, it's pretty stable. That means that you use again only the extreme data, the top 100 or top 200, and you find a value of about 0.032. It's a little bit more. And this also seems to be reasonable with intuition if you think about the data of the last 6 years. Maybe because of the time I will skip this or only go briefly into this. Some people say you should not look at var or related quantities because it gives you only one value in the distribution, but you should look at the mean given that you have a high value. So you should look at what's called the expected shortfall. Some people call it tail var, C var, or expected tail loss. So basically you look at the expectation, at the mean of the risk, given that the risk is above a high value. And with some elementary probability theory you can calculate this quantity, and everything which you do not know you give it a head, and then you can do some calculation and you basically can find an estimate of this with extreme value theory. And you see that the estimate at the end looks more or less the same as the estimate for the var, but you only have to divide, if you look at the very end, by 1 minus gamma hat. So you see that again, gamma, this extreme value index, plays a crucial role here. Finally, one more slide. Quite often you are only interested in extreme values, but it might be that you are interested in the whole distribution, so that the tails matter, but that also the central part of the data matters. If that's the case, my recommendation is to glue together an approach that deals with the central part of the data and our extreme value approach. In particular, when you use for this central part of the data a non-parametric approach, the so-called empirical distribution function or historical simulation, then this gluing together goes in a continuous way. So that means that if you look at the distribution function in the central part and the distribution function in the tail, then at the point where they meet, they give you exactly the same value, which is very nice and reasonable. So my last part, I just said it, it's about tail dependence. That means that we look at more risks together. So we are not looking at a sample of one-dimensional risks, but essentially we're looking at two or more risks. And for simplicity, let's look at two risks. For instance, you can think of daily losses of 2 shares. And what we do is, for every risk, we look at its own scale. So that means that we look at the probability that risk X is above its own quantile at 1 minus p. And if we forget about this, then this probability is by definition, it's just p. That's how we made it, right? So we have two events which have probability exactly p, which is a given small number. Assume that we know this q1 1 minus p and q2 1 minus p. But what we want to know is the probability that they are both happening. This is an important question. As I just said, it has nothing to do with the marginal behavior of the risk, so it has nothing to do with the tail heaviness, but it only has to do with the tail dependence. So there are two things. One is the severity of the tail heaviness. The other one is the tail dependence if you look at more risks. And extreme value theory gives the notion of tail dependence or tail independence, and I claim that this is the proper notion for quantifying dependence at extreme levels. So the concept of correlation is not very useful here, since it uses again the central part of the data and it does not focus on high levels. So here's a quote of the Global Financial Stability Report, April here. It says for a non-parametric measure of joint tail dependence based on multivariate extreme value theory is defined in order to quantify the possibility of common extreme shocks. This method of measuring tail dependence is better suited to analyzing extreme linkages of multiple entities than the traditional correlation-based approach. And let me prove this by picture. On the left, there is a data set. These are real data. And these are losses, actually indemnity payments of an insurance company on the horizontal axis, and on the vertical axis there are AEs, which are loss allocated expenses like payment of lawyers and investigation expenses. And on the right there is a simulated data set from a normal distribution which has the same means, the same variances, and the same correlation. Also the same correlation. And what's tail independence? Tail independence is a weaker concept than independence, and it roughly says that very high or very low values of the risks, that they do not go together. So in case of tail independence, they do not go together. In case of tail dependence, they do go together. I will come back to this data. So if you have complete independence, then of course it's easy to calculate the probability we just had. It's P times P, that's the definition of independence, so it's P squared, it's very small. But if we look at this from a conditional point of view, you can ask yourself what's the probability that the first risk exceeds its threshold, given that the second risk does. And if we use this, if we calculate this using conditional probabilities, we get exactly P. And this is not a surprise, of course, because if we have independence, the condition doesn't matter. So you only have to look at the unconditional probability, which is just P, right? And this P is very small. And it's too obvious to say if P goes to 0, then P goes to 0. But if P goes to 0, then this outcome goes to 0. But it doesn't always go to 0 with P. If you look at the general case, it might be, and that's our definition, we say that X and Y are tail dependent if for P tending to 0, this conditional probability of the previous slide goes to a limit. So there are two possibilities. It goes to a positive limit or it goes to 0. If it goes to a positive limit, we call it tail dependent. If it goes to 0, we call it tail independent. So that's a much weaker assumption. And now there is the strange thing that if you look at the normal distribution, the bivariate normal distribution, then whatever the correlation is, whatever correlation you take, there is always tail independence. So the correlation doesn't tell you anything about tail independence or dependence. Actually, for every normal distribution, you have tail independence. So the normal distribution, which is very popular, is for many applications, especially if you consider the tails, is a very bad distribution because it has the wrong tail heaviness typically, and it also has the wrong tail independence or dependence properties because it always has tail independence. Here's another quote. The problem with the models is that they do not assign a high enough chance of occurrence to the scenario in which many things go wrong at the same time. And these models are the normal or Gaussian models. So extreme value theory can be generalized to this multivariate case, and actually this limiting distribution G, it can be decomposed in the two extreme value integers and a so-called spectral measure. And this spectral measure quantifies the dependence of extreme risks. So it can be seen as a tail version of the correlation, or better, of the copula. And there exist good estimators of this phi. And again, this approach is useful for risk management. More classical approaches, and I just said that, based on the correlation or the normal distribution, may fail dramatically. I have a few pictures here. These are again the data I just showed you, the loss AE data. So losses and allocated expenses. Yes. And we had this normal data. And what you see from this picture, and I have to explain what this is an estimate of this spectral measure or angular measure. And in case there is tail independence, then this function in the middle should be more or less flat. And if you see the dashed line, which comes from the normal data, then you see in the middle between 0.3 and 1.2, for instance, that it's more or less a flat function. So that means that you have tail independence, what you always have for the normal distribution. However, if you look at the real data, this loss AE data, then you see that there is a very strong increase of this spectral measure in this situation. So that means that here you have tail dependence. Here is a similar data set with height and weight. This is the National Nutrition and Health Survey in the US, more than 2,000 data. You see that there is a correlation of about 0.3. So that means that in the central part of the data, that height and weight, that they go together, that there is a correlation. The longer, the heavier in a regression sense. However, if you look at the spectral measure, then you see that it's very, very flat in the middle. There is complete tail independence. Yeah, that's perfect. 1 minute.
Sure.
What's the message? 2 messages. One message may be interesting for a birthday party or so. Nobody can run the 100 meter faster than 9.51. No woman can run faster than 10.33 with some uncertainty. This is statistics. And more important, there is something out there called extreme value theory. Basic concepts are extreme value index and tail dependence. And this might be helpful for forecasting extremes in financial accounting and related fields. It's about extrapolation. It's statistics. It cannot do magic, but it can maybe do a lot better than empirical curve fitting or other ad hoc methods. And that's about it. These are 3 books on the subject I can recommend. And these are some papers. The first 2 papers are the papers which are in the conference material. The third one is a follow-up on this athletics. And then there are 2 papers on finance and 1 paper on actuarial applications of extremes. Thank you.
Okay, thank you very much. May I open up for questions? Yep. Christian.
Right.
And extrapolate from there. But as you said, there are choices like what do you make the K? How far do you go out in the tail when you start extrapolating? How do you evaluate these things? So sort of what are good or because in the end these are still estimates, and one of the issues that you're going to run into is the further you go out in the tail, the fewer observations you're going to have, and at some point you're going to have very little to evaluate. So I'm just curious what kind of methods you would bring to bear and how you evaluate the sort of the quality of the estimates that you're getting, which ultimately I think is pretty critical, especially once you start getting into the dependency issue, where you're going to very rarely observe cases where this market blows up and this market blow up together kind of scenarios.
Yeah, interesting question. So indeed, as you say, if you take assume that you have 1,000 data, just to make it practical, so you can do several things. You can make K very small, 10 or 20. And then you have a large variation or a large variance. So typically, if you look at a plot, although the plots I showed, which were real plots, they were quite nice. But typically, if you look at the plot of estimators against K, then in the beginning it's very wiggly. And then you have a kind of a stable part where you should choose your K. And then it typically goes up or down, which means that you are too much in the central part of the data, so that a bias comes in. So it's basically a question of a trade-off between bias and variance, and so that's describing the problem. Describing the solution is, as usual, a lot more complicated, but there are several techniques. One of them is a so-called double bootstrap technique to find this optimal case. So we typically look for quantities like the extreme value index. We look at a so-called mean squared error, which is a measure of characterizing the error we make, and then we try to find that k which minimizes this error. And as I just said, there are some techniques for doing that. The easiest technique, but that's not very satisfactory, is to just look at the picture and look for a first stable path. But that doesn't give you a measure of the uncertainty you have. So in order to have a more formal answer, you should work with these more formal methods, which I just mentioned.
Other questions? Yep.
You had given the example of the graph of just looking at the time trend in world records, where there seems to be some information and improvements there, whereas the method that you have doesn't seem to take into account some time period specific innovations. And I'm wondering whether there's some hybrid blending that is either in the literature or that could be brought to bear here, because obviously the existence of Usain Bolt right now is additional information that you're not really factoring in. You're giving the same weight to an observation of Usain Bolt running 9.7 last in 2000, or sorry, let's say 9.8 in 2007 to someone else running 9.7 in let's say the year 1995.
Yeah, that's right. Yes. It could be an option to try to do some kind of discounting and to give more weight or less weight to an observation in 2008 than to an observation in 1995. It's very complicated to kind of adjust for this in the tails. Maybe you can do that easily in the center of the distribution. So what we assumed, and maybe there is some room for improvement there, what we assumed is that this relatively short period in athletics is a kind of stationary period, since it's only a period of about 15 years. But I know that in other sports like speed skating, which is very popular in the Netherlands, but also in swimming, that there are so many technical developments that you should not do that.
Okay. Eddie.
I had a slightly different question from Christian's, but related. It's the question about the choice of n as opposed to k. So, for example, if you chose instead of the top speeds for professional runners, if you had used us as kind of the sample, the n that you draw from, is that going to affect the type of extremes that you're going to observe statistically? So, is the choice of n actually a very important decision within this, and what guides that decision?
Well, in general, we do not choose n is given to us. But in this case, we try to make n, which is not really n. So normally, if you look, for instance, at stock returns, and you look at 1 year, you have, I don't know, 250 data or so, and that's it. But here there are basically 6 billion data, although for not all of us the 100-meter time is recorded. But basically, n is 6 billion here. But we only took as many top order statistics as we could get, and we ended up at 760 or so. But it would have been helpful to have, instead of 700, maybe 10,000 data. But still, then you have to choose this optimal k, and it might be, even if you have a list of 10,000 personal best, that the k which you choose for estimation is 300 again, and then it doesn't help you that you have more data.
Maybe let me try to rephrase the question a little bit. So if you had the data available, are you going to get different outcomes? If you had the data for all 6 billion people, as opposed to just the top elite runners in the world, then you try to run your estimation process.
Yeah.
Are you going to get different estimates depending on what type of scores that you're using?
It depends on the data, but typically you don't get different estimates because you only use the top performances for prediction. Yeah, so it doesn't help me if I know that I can run the 100 meters in 15 seconds because I'm in the center of the distribution.
So then, just very last question following up to this. So if we were trying to predict extreme outcomes related to firms, for example, would our interest be in getting the entire population of, say, publicly traded firms, or would we be more interested in trying to look at extreme performances, firms that are nearing bankruptcy or something like that? Are you looking for firms that are more likely representative of what would be kind of a tail type performance?
Yeah. So if there is sufficient homogeneity, I do not know that, but then you only need the upper order statistics. Yes.
But these firms are dependent of each other. I mean,
Yeah.
If a good performance in one firm,
Yeah.
and if then the other firm goes bankrupt, the other firm, the good performing firm will lose out.
Yeah. So I have not touched about the issue of dependence.
Yeah.
So what I assumed are that my data are independent.
Right.
If they are dependent, you need more complicated models, and what you could do then, and that's what I said in the beginning. This is an introduction. What you could do then is take some appropriate time series model like a ARCH or a GARCH model,
Right.
and then consider the innovations of this model as being IID, and then do this procedure, and then go back and then put this back in the model again. Yeah.
I asked a question. I should not have done that because Russell was standing there. Russell.
I'm concerned about the tail independence of the normal distribution, which is one that we all use quite a bit. So let me give you an example that would ring true to this conference. We have signals about stock returns. And so we have two variables, the return and the signal. And we would model those, I think all of us would model those as being jointly normal. But as I understand your result, when I get to the tail, they become independent. So
Yes.
for instance, I'm trying to find the stock with the highest expected return, the one with the biggest signal. I would in fact be at a place where there was no longer a relationship between returns and signals. That's what the result says?
So of course this was, the way I stated it was a little bit theoretical. So of course it does matter if you have a normal distribution with a correlation of 0.2 or a correlation of 0.8. But if you look in the limit, if you really go to the tails, but for 0.8 you have to go further into the tails than for 0.2. But if you go to the limit, they are all independent. But maybe for 0.2 you don't have to go that far in the tail of the distribution. For 0.8 you have to go pretty far to see this tail independence.
Okay. So it still
Final
leaves you, I mean, the ultimate conclusion is that once you've found the most valuable modeled stock, right, that it's unlikely to actually be the stock with the highest return.
Yes, yeah. So maybe, so if you look at the normal distribution and if you have a correlation of 0, this calculation holds, it's very easy, and you get P as an outcome. So if you have a correlated normal distribution, you get P to some power. And this power depends on the correlation in a very easy way. But still, if P goes to 0, this expression goes to 0. Whereas in the case of tail dependence, it goes to a non-zero limit.
All right, thank you.
Okay. Well, I think we have to wrap it up here. Thank you very much, John, for this very clear presentation. Thanks a lot. And, we have a break now, and we reconvene at 2:40. What is it? Sorry, at 10 past 3.